Okay, so today what I want to look at is rational functions. Rational functions are really just in the form of f of x equals p of x over q of x. Now, there's a really simplistic version of rational functions that's actually just called inverse variation. It comes from a constant, any number, divided by x. And if we think of it like that, and especially if we think of 1 over x being the parent function, we can simply translate the parent function over and up and stretch it out one way or the other, and the math actually becomes relatively simple. So today, we want to be able to know what the inverse variation formula is. We want to be able to create some tables of values so we can kind of come up with our points. We want to be able to graph some different functions. Just a sec. So when we're looking at this, p of x, which is our numerator, will be equal to 1, and q of x will be equal to either x or, as we translate it, potentially x plus or minus a number. Thinking about some of the vocab that I'm going to use today, you're going to need to know what a branch is. Rational functions are not continuous graphs. They force you to essentially pick up your pencil and start over somewhere else. Each time you pick up your pencil and put it down somewhere else, you're creating a new branch. Okay, so it's each piece of the function. Again, a rational function is the quotient, meaning division, of two functions. P of x is the numerator, q of x is the denominator. A point of discontinuity is going to be created whenever the graph is discontinuous or discontinued as you think about it. So anytime I pick up my pencil and have to start the graph again would be a point of discontinuity. What we have to realize is a branch is the graph, or each piece of the actual graph, and a discontinuity is every place between those branches. We have an asymptote. It's a type of discontinuity. We normally draw it in with a dashed line, and it's a vertical or horizontal, potentially a slant asymptote that the line your graph will approach or never touch. And it can either approach it like this and then just stop, or it can approach it and curve away in that manner. It just can't touch that actual line. A hole is formed at a place that the graph is undefined, but it's a special undefined point where both the numerator and the denominator would be equal to 0. So we do know that, say, a vertical asymptote is when your denominator equals 0. Horizontal asymptote, there's a few more pieces to figuring that out. But the hole is when I could put a number in for x and both numerator and denominator would equal to 0. So we're going to start out where we're not going to really see any holes because there's no x's in the numerator to create that. But what we want to do is graph the following two rational functions, and these are actually inverse variation. Inverse variation is typically written as y equals k over x. And the translation of it is y equals k over x minus a plus b. Now, what made it stick for me was to think of a and b like similar to h and k in the vertex form of a quadratic. So when I think about a quadratic, the h comma k is my vertex, and I know it starts at 0, 0 in the parent function, and the h shifts it horizontally, and the k shifts it vertically. And so a lot of times you'll actually, in my particular class, I'll use an h and a k there just so we get a consistency of what these numbers are doing, because they're really doing the same thing, which is translating our graph. Well, let's start by just finding some points for these guys. And as I look at this, I want to come up with 8 different points. And I'm going to call this my x, and this 2 over x, and this 9 over x. Well, the only number I know I can't put in really is 0. That's going to make both of these undefined. What that means is when x equals 0, we have, remember our denominator equaling 0 will form a vertical asymptote. So where is the line x equals 0? It's right there. So what I'm going to do now is I'm going to pick some different numbers. I'm going to pick, let's say, -4, -3, -2, -1, 1, 2, 3, and 4. So this becomes 2 over 4, which is, or 2 over -4. So that's going to be -1/2. This is -2/3, -1, -2. As I go forward, what I notice is now when I put in the positive, I'm just going to kind of flip it around. So that what I get is something like this. When x is -1/2, y was -4. When x was -1, y is -2. X is -3, -2/3. So now we're kind of getting smaller. And what we see here is that I get a graph, or a branch of my graph, that looks similar to this. Over here, I'm going to see essentially the same thing. So I've got 1, 2, 2, 1, 3/3, 1/2. And you get something that looks like this. Alright, well, that's my graph of 2 over x. Well, if I want to graph 9 over x, it's still undefined at x equals 0, so that's going to be right here. But now I've got 9 over -4, so this is -2 1/4. This is 9 over -3, so that is -3. And I see all these are going to be negative. -4 1/2 and -9. Again, I know this is going to just flip the signs. And so even though 8 points seems like a lot, really all I'm doing is 4 and then flipping the signs. And that comes, I don't always have to use the same numbers, but it makes my life easier. So as I graph this, now when I go to -4, instead of being at -1/2, I'm all the way down at 2 1/4. Okay? When I'm here, -3, -3, -2, -4 1/2, -1, -9. And so I'm going to get something that looks like this. Now both of these lines will never cross this here. That's our horizontal asymptote. We do know that, again, because the degree of the denominator is greater than the degree of the numerator. Over here, you're going to see the same thing. 1, 9, 3, 4. And it looks like this. So what we notice here is really important. We do see that this point is the center of both graphs. It's equidistant from these two. I know my graph isn't perfect, but you kind of get the idea. We see that having a larger number in the numerator sort of pulls this middle away. But that in the long run, as we approach infinity out here, or as we approach 0 in the middle, so like really tiny numbers for x, we're going to see the same general behavior. The translation is just going to take this center dot and it's going to move it over and up, or over and down, or over and up in those directions. So let's look at a couple translations. So as I graph these three, what I see is I had my original 2 over x, and I'm just going to sketch that one in. And I knew that I had a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Well, let's look at this first one here, y equals 2 over x plus 3. What this plus 3 will do is it's going to shift my graph 3 to the left. It always kind of goes in the opposite direction because we know it was x minus h in the denominator, or x minus a as many books call it. So what happens to my vertical asymptote is my vertical asymptote becomes x equals -3. This doesn't have a number out here, so it does not change my horizontal asymptote. This line ends up looking just like that. Now, how would I go from, say, my x's of -4, -3, -2, -1. We know 0 is undefined. 1, 2, 3, 4. In 2 over x to 2 over x plus 3. Well, if this was -1/2, -2/3, -1, -2, 2, 1, 2/3, and 1/2. Well, all of these numbers, all I have to do is subtract my y value, right, is going to stay the same for this particular one, but all it's going to do is shift this left. So now instead of having a point at, let's take 1, 2, because that's probably the easiest. 1, 2, a really big comma. This point shifted left to here. It is now, well, if a left shift is going to affect this, it is now -3, 2. So now I know -3 is going to give me 2 there. As I look at -1, -2, about right there, this also shifted left, and this goes to -4, -2. So when I put in -4, I'm getting -2. And so these points are all going to shift left. It's going to change what my output is on that one right there. To look at, just to keep this video somewhat concise, just to look at this +5. This +5 is where that, if we look on our last slide, where this number is here. B will become your horizontal asymptote. So in these, it's +0, hence my horizontal asymptote of y equals 0. Whereas here, my horizontal asymptote should go from y equals 0 up to y equals 5. I'm going to try and get a color that stands out a little more. Let's go with orange. Alright, so now not only have I shifted it, in this case we'll make that a plus so we don't have to shift it twice. That not only have I shifted it left 3, but I've also shifted it up 5. So now my graph would come in and be right in here. So if this is 2 over x plus 3 plus 5, remember opposite direction for the denominator, so that brought us to here. Same direction for the numerator, that's going to bring us up to here. Now this point, which had gone left 3, is now going to go up 5, which is going to change my y value. Negative 3, comma 7. This point went left 3, it is going to go up 5. So this point becomes negative 4, because it didn't change my x value. And you have to think negative 2 plus 5, that's going to give you a positive 3. And so the numbers change, but as long as this center dot right here, if I think about what this did in total, it went from over this way, 3 units, and then it went up this way, 5 units. So the new center dot is right there, and that went negative 3, comma 5. It's kind of your center, and I always encourage drawing your asymptotes first, and then just putting in your branches. Because when you're doing this by hand, you kind of end up just kind of sketching in your branches as best as you see fit. I know it looks a little messy now, but hopefully you got the idea of how to translate the parent function of inverse variation or the parent function of a rational function, which are the same thing.